Hello and welcome to this video about determinant proofs. In this video we'll prove that any square matrix that has a row of zeros has a determinant of 0. So now to start this proof, we'll let matrix A be a square matrix with a row of zeros, and we'll locate this row of zeros at row P. The matrix obviously has to be a square matrix, because only square matrices can have determinants. And we'll let another matrix B be the matrix we obtain by multiplying row P of matrix A by a constant C. So from a past theorem we can get this equation about these determinants. The determinant of B is this constant C multiplied by the determinant of A. But multiplying the row of zeros by C doesn't change this row. It remains a row of zeros, so these matrices A and B are equal. And because these matrices are equal, then their determinants are equal. We can use these two equations to get this equation, that the determinant of A is equal to a multiple of itself. And assuming that C is anything but the number 1, then the only solution is that the determinant of A is 0. Using the constant C implies that it must represent any real number and must be true for numbers that aren't 1. The textbook multiplied the row by 0, which would change the matrix if it didn't multiply a row of zeros. But any non-1 number could be used in this proof. So I'll prove this another way that's longer but should provide some intuition. We'll set A to be this in ijth entry notation, but we won't use the square brackets. We'll only use the entry variable. And this is the property of this entry of A, that when the row indice is P, then this entry is 0. This implies a row of zeros at row P. We'll expand out the determinant of A using the definition. The sigma variable represents the permutation dummy variable and represents all of the permutations of size n. We'll expand it out a bit more, showing the location of the entry at row P, with rows above and below shown, but this should work for 2 by 2 matrices, even though there's 5 entries shown. So we know that this row contains only zeros, so we'll substitute the 0 in here. We can then take the 0 out of the sum because it's in every product in the sum. And this is obviously equal to 0 because of the property of 0, that any number multiplied by 0 equals 0. So we've proven this theorem a second time, and I hope it's more intuitive this time. So I just want to show you this picture. This is a 3 by 3 matrix with a row of zeros. If we calculate the determinant of this matrix, we'll always get a 0 in the determinant product, because we always have to get an entry from every row. And so we'll always get an entry from the row of zeros in each product. So I hope that you can see it now, how this row of zeros forces the determinant to be 0. So I hope that you found this video to be helpful and educational. Please click like and subscribe if you did. Feel free to write anything helpful in the comments and to share this video, and thanks a lot for watching.